take out some paper, write some stuff down with me here. We are going to learn some stats. Whew, I've been talking forever. What time do I got until? 55? 1:55. It's 1. All right. We're good here. I'll go quick. Shouldn't be that bad. So, what are we doing today? First off, we're going to take a look at the difference between a statistic and a parameter. All right, the difference between a statistic and a parameter. And that's going to help us frame the topic of this new thing, the sampling distribution. And yes, the ling is important. You have to say it that way. The sampling distribution. All right, so we need to understand what a sampling distribution is. Like, what the heck is this thing? What's the ling? We got to figure out what it is first. We might create some small ones. That's not super important. The main thing is we're going to use them as evidence to support or refute claims. Okay? The sampling distribution is really something we can use to support or refute claims. So, you've got, again, your video, which, like usual, take notes, take a picture, upload to Teams. And then you've got that new fancy homework assignment on the website. Okay? All right, let's do this. Statistic versus parameter. So, statistics are only with samples. Okay? You take a sample, and the numbers you get are statistics. If you're talking about an entire population, like you take a census and you ask everybody, those are not statistics. Those are parameters. Statistics are only in relation to samples. And so oftentimes the statistics we look at are the mean. And when we talk about these, we use English letters, right? So that is X bar. If we're talking about the mean of a population, that's where we use the Greek, right? So that's mu. And then the standard deviation. Again, English character, so that's usually S sub X. And the standard deviation for a population, we use the Greek, sigma, lowercase sigma. And, it's not always the mean. Sometimes it is a proportion. And so for a statistic, we use p hat. Why do we use? All right, we'll get there. Why? Proportion is p hat, and if it's a population proportion, we use p. Bolt, you say we use Greek letters? 2 out of 3 ain't good enough, man. Every good rule has an exception. We can't use the Greek letter p for proportion. It's taken. Here's the Greek letter p. Pi. Math already took that for other things, right? So we can't use the Greek letter p for proportion. That would just be confusing. So the way we distinguish that is regular p for population proportion, p hat for sample proportion. All right, let's take a look at an example where we're going to identify both of those. So the Gallup poll asked 515 randomly selected U.S. adults if they believe in ghosts. X-Files. Of the respondents, 160 out of the 515 said yes. All right, we got a nice little sample here. Identify the sample and its statistics and the population and its parameters in this. So let's do it. So what is our sample? So our sample is the 515 randomly selected adults that responded. That's our sample, those 515 people. What is our statistic? 160 of the 515 do believe in ghosts. Now, usually, actually, that's not reported that way, 160 out of 15. Usually, we would turn that into a proportion. So what is 160 divided by 515? 31%. So usually, we'd report that as p hat as 0.31. That's our statistic. All right. What about our population? So our population here, well, what did we sample from? The population and the sample should go together a little bit because you sample from the population. So if our sample were the 515 adults, well, our population is also going to be the adults, but all of them. All adults in the U.S. As it said, they were selected from U.S. adults. All right, and our parameter. So here we don't know what the parameter number is, but we know what we're trying to find. We want to know the actual. What is the true proportion of all adults in the U.S. that believe in ghosts? Now, a couple of things about that sentence, actually. There's a few important words in there that I want you to try to emulate. All right? The word true. That helps me see that you are actually talking about the entire population and not the statistic. Okay? The true proportion, the actual one, not the sample, but the actual proportion. And then the other word that helps me see that you're talking about the population is the word all. If you're talking about a parameter, you really want to try to use those words. All right? That will really make it clear that you're not talking about a statistic. You're actually talking about the population. The words true and all really help with that. All adults in the U.S. The true proportion. That really helps. All right. I want you to try this out. So we're going to head on over to the Desmos, period 5, right? Throw that link into chat for you. I got one that I want you to try. Just slide one real quick. Head on over there. Try that out yourself. Make sure you can identify the sample and the statistic population parameter. This one's a little tricky, actually. Yeah, for sure. The difference between p hat and p. That is just the sample versus population. So if it's a sample, you use p hat. It doesn't mean anything different besides, it's still a proportion. What percent of blankety blankety blank happens. But because it's a sample, we put the hat over there to say it's a sample. If it doesn't have the hat, you are referring to the entire population. So like in my ghost example, we don't know what P is. We only know what P hat is. We do not know the true proportion of adults in the U.S. that believe in ghosts. We don't know that. All we have is the sample P hat. Population parameter is just the number that refers to the population. So The parameters are mean, standard deviation, or a proportion. Those are the parameters. So if you're talking about the mean of a population, that's the parameter. If you're talking about the mean of a sample, that is a statistic. So a parameter is a statistic for a population. That helps. There we go. All right, so next, sampling distribution. What the heck is a sampling distribution? Well, that first comes from this idea of sample variability. Okay, we've talked about this a little bit, but let's remind ourselves. What the heck is sample variability? It's just the idea that all samples are not the same. So if I took another random sample of 515 people, and I asked them, do you believe in ghosts? Do you think exactly 160 of them would again say yes? Hopefully you realize, no, probably not. It wouldn't be exactly 160 out of 15 again. No sample is going to be exactly the same as the previous sample. We think it might be close, but not exactly the same. Similarly, with the castle example, if we took another sample of 20 random temperatures, 20 random times and took the minimum temperature, do you think the minimum would again be 38 degrees exactly? No. It might have gotten a little lower. It might have not gotten quite as low. It'd probably be similar to 38 degrees, but it wouldn't be exactly the same. That is the idea of sample variability. Okay? So I've got the definition here. Different samples of the same size from the same population will not be exactly the same. I'm hoping that kind of makes sense. Yeah, if you take another sample, it'll be a little bit different. Similar, I hope, but a little bit different. And because they all have a little bit of variability to them, that's where we get the sampling distribution. So the distribution of values taken by a statistic in all possible samples of the same size from the same population. That distribution is what we call the sampling distribution. And like most mathematical definitions, you're probably like, Bull, that doesn't make any sense. I don't know what the heck you're talking about right now. What? All right, most math definitions are kind of like that. A visual will help. Okay, so let me show you what a sampling distribution actually is visually. And of course, food is how we do that. Y'all love Reese's Pieces? Gotta love me that peanut butter. So, let's say I have a massive jar of Reese's Pieces. Okay? And I'm gonna start sampling candies. Now, I'm not gonna eat them. I'm gonna take them out, and I'm gonna count how many oranges there are, orange pieces there are. Okay? So let's say Reese's Pieces says that the probability of an orange, or the proportion of orange, the true proportion of orange is, 37%. Let's say 37% are orange, according to the company. I'm going to sample 25 of them. It's probably about one serving size, don't you think? So I'm going to draw those samples. So I'm going to sample. There are my 25 candies. They pop out of the machine so nicely. And there were 13 orange ones. Okay? So I'm going to turn that into a proportion. 13 out of 25 is right around, what is that, 50% maybe? And I put a dot on a dot plot for that proportion. And that's the interesting thing now about a sampling distribution. The dot plot, the dot in the dot plot represents an entire sample. Not an individual, but an entire sample. So this dot right here represents the proportion of orange in an entire sample of 25 Reese's Pieces. Then we do it again. Ooh, that sample was much lower. Sample variability. That one was only like 30% orange. Then we do it again. We get another dot. That one was a little less than 40%, maybe 38 or something. Very close to the true proportion, actually, isn't it? And we do that over and over and over again, but we don't animate it. Let's do 50 samples. Much faster. Here we have our sampling distribution. It shows the distribution of all the samples and the shape it takes. Now again, each dot is not an individual. Each dot is an entire sample. And we keep going. Whoa. What shape do you see there, ladies and gents? What does that kind of look like to you? If I take a look at that shape, what is that? Oh man, you might be able to see where this is going. What kind of questions is Bolt gonna be asking you later?
The numbers don't lie, and they spell disaster for you.
Sorry, I had to. So that is a sampling distribution. All right, one other that I want to show you, okay? So this is going to be with means instead of proportions. So we're going to have some population here. I'm going to make it skewed to the right. So there's my population. I'm going to sample out of the mean. I'm going to take 10 as my sample size, all right? I call this the the poop animation.
Bazinga!
You can see why it's called the poop animation. So we took a sample, and then we recorded the average of that sample. Then we do it again. We take another sample, and then we plot the average. We do that over and over and over again. Sidebar real quick, sidebar. You can't just say the distribution anymore. If you say the distribution, I have no idea what you're talking about. We have a population distribution. We have the distribution of an individual sample. And now we have a distribution of all the samples, the sampling distribution. So if you say the distribution, I got no idea what you're talking about. You have to be very specific about which distribution you're talking about. But we do this thousands of times to build up our sampling distribution here. So those are all of our sample means. We now have a sampling distribution. Look at that shape. That looks so familiar. All right, that's what a sampling distribution is. How are we going to use it? Okay. So first, we have to be able to interpret a sampling distribution. And by that, I mean interpret what one dot means. So here's my example for you. Suppose the Gallup poll conducted their survey about ghosts 100 times, then made a dot plot of the statistic for each sample. Okay, so these are approximate sampling distributions. I have to say approximate because a sampling distribution would technically be all possible samples, not just 100 of them, all of them. But I made a approximate of 100 of them to get us an idea. So on the left, we've got the frequency. That's the number of ghost believers in a sample of 515, but usually that will be reported as a proportion. So here it's turned into a percent, that's all. Same information, but the right one is what we usually get. So there is one dot at 0.25. What the heck does that dot represent? So, remember, each dot is not an individual, it is a sample. So that means in one of the samples of 515 people, all right, it was an entire sample of 515, 25% of the respondents believed in ghosts. All right, that's what the single dot means right there. It's an entire sample, 25% believe in ghosts in that sample. It's the first thing I want you to be able to do with sampling distributions, interpret what the dots mean. Hopefully that's not too bad. Next thing we want to be able to do with it is support or refute a claim. All right, so example 2. Mrs. Bolt gives her students time in class to start their homework. Man, she's so nice. Bolt, why can't you be like that? Because I'm the mean one. Can you believe that? Would you believe that if I was the mean one? I don't know. To determine how much time they get, she has a student select a simple random sample, remember SRS, simple random sample, of 20 poker chips from a large bag. The number of red chips determines how many minutes they get. Mrs. Bolt claims there are 100 red chips out of 200, which would give us a population proportion of 50%, 0.5. Jenna selects an SRS of 20 and got 7 red chips. What? Jenna cries. BS. That's bad statistics, remember? Bad statistics. So, give 2 explanations as to why Jenna, poor Jenna, got only 7 red chips. So there's 2 plausible explanations. The first is that Mrs. Bolt is full of beans. All right? The first one is that Mrs. Bolt lied to us, and the true proportion of red chips is not 0.5. It's possible. She could be lying. The other possibility, Jenna drew only 7 red chips because of sample variability. All right, maybe just it happened to be low that time. She got unlucky. Okay? Those are our 2 plausible options. And so we have to use the sampling distribution to figure out which one of those is the way to go. All right? Was she just unlucky, or was Mrs. Bolt lying? So we're going to go back to Reese's Pieces for this, okay? Doesn't really matter what color you're looking at. So the probability of orange, don't care about the color. Think of that, the probability of success. Mrs. Bolt says it's a 50-50 chance, so I'm going to leave it at 0.5. How many chips are we drawing? Only 20. Okay, and I want a good sampling distribution, so I'm going to put this up at like 5 hundo. I do not want to animate that. That would take forever. Okay, so this is going to give me a approximate sampling distribution of what samples could look like if, in fact, the true proportion was 50%. So here is my, let's go proportion. Let's snip that. And put that in the OneNote for us. That way when I push this out to you, you'll get a nice complete picture. There we go. All right, so questions I want you to be able to answer. Let's see, there is one dot at, I don't know, let's just pick one. There's a dot at 0.6, right? There's lots of dots at 0.6. There is one dot at 0.6. what does this dot represent? All right. That means there was a sample where, what does the 0.6 mean? 60% of the chips drawn were red. All right, that's my context, right? I'm drawing red chips. The proportion is the proportion of red chips. So there was a sample. There were lots of samples, it looks like. Lots of samples where the proportion was 60% red. There was a sample of 20 chips, I guess, huh? Poker chips. Context, 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 Bolt.
No.
You are out of practice. All right, so would it be surprising to get a sample proportion of 7 out of 20, or 35%?
This glass so we can play in here.
Would that be surprising? So I come over to my sampling distribution, and I find 35%, which is what, right here? So these are all the 35% or less. Now I go or less because Jenna cried foul because the number was too small. All right, there's no way I'm only going to get 7. You would never get 7. That's too low. So we take a look at what are the chances of getting 7 or lower. Well, there's quite a few there, aren't there? That's 2 pretty large bars and some trickling ones off to the side. Yeah, that definitely happens. So I would not be very surprised if this happened. If a sample had 35% or less red chips, because in our sampling distribution, this happened plenty of times. All right, it's not weird for that to happen based off of simple sample variability. So therefore, does Jenna have convincing evidence that less than half the chips in the bag are red? Does she have evidence that Mrs. Bolt is lying? No. There is not convincing that the true proportion is not P equals 0.5. Let me move this out of the way. Because a sample proportion of 0.35 is very plausible simply due to sample variability. I want to fit that in there. Sample variability is sort of the reason why. It could definitely happen that you get something that low. See, we had some way down here, down to 0.2. That could definitely happen when we know the true proportion is 0.5. All right, those are sort of the 3 things I'd like you to be able to do, ladies and gentlemen. I don't think we have time to head over to Desmos again. If you want to take a look at that, it is good practice. But we only got 4 minutes here. So, sampling distributions, okay? Each dot is an entire sample, not an individual. And then you want to be able to interpret the evidence there. Could something occur just because of sample variability, or is it so outlandish that, no, I don't think you'd ever get that. Like if she only got 1 red chip, 1 red chip would be 5%. Is that plausible? No. Up to the sampling, yeah. How far up do I have to go? There it is. So if it's not in your sampling distribution, well then it's not plausible to happen because your sampling distribution has all the possible samples. All possible samples. So yeah, like if that red chip one, if she'd only gotten one red chip, that would then be evidence that Mrs. Bolt is lying, because one red chip never happened in our sampling distribution. Nothing went that low. Because I think one out of 20 is 5%. Yeah, 1 out of 20 is 5%, and that never happened. That's too low. All right, let me push this out to you so I don't forget. Distribute, Unit 5. So if you head over to your OneNote, you should now have a Unit 5. You should now have Lesson 7.1 in there. The course stuff that I went over is also there as well. But for homework, you've got your video. Again, take notes as usual. Upload the picture as usual. And then your homework is from that online textbook. I will fix the due date time. Yeah, I don't want it to be 12 a.m. So I will fix that for you. But I think it will be 9 a.m. because I don't want you doing it during your first or third period class. So, all right, ladies and gentlemen, that's all I got. Have yourself a great day. If you had any issues with anything, I'll stay on the line here a little bit longer, but we are back in the thick of it. Good luck to you all, and I will see you on Thursday. Bye, everyone.
Thanks, Mr. Bolt. Have a good day.
You too.
Have a good day.
Bye, Mr. Bolt.
Bye.